Hey everyone, this is our video on physics, constant motion, the basic kinematic equations. So here's a rough outline of what we're going to be going over today. We have graphs of motion, the position time graph, the velocity time graph, the acceleration time graph. We're going to compare each of them side to side and explain how they're related to one another. We're going to briefly go over the kinematic equations, what the variables represent, which variable is missing in each, and how to manipulate these in order to solve problems. Over here is a little diagram of what you can use, a type of problem that you can use the kinematic equations to solve. So let's get started. Alright, so first of all, there are three different graphs of motion as seen here. First, there's a position and distance graph. This one's pretty straightforward. Over here we have our buddy Mario, who's going for a run, okay? Imagine Mario starts at point 0. He starts over here. Once the timer for the race starts, Mario runs in a straight line away from the start. As time goes on, he starts over here, he starts running this way, and as time goes on, his position is graphed, right? So at 5 seconds, Mario appears to be 60 meters away from the start point. At 10 seconds, he appears to be 120 meters away from the start point. But at 15 seconds, something changes. Mario realizes that he forgot to tell everyone where he was going, and he decides to turn around. His distance starts going down. He starts running back to where he started, as seen on the graph. Around 25 seconds, he's about 60 meters away, but he decides to take a break. So let's take a small recap of the position graph. Increasing into position means that the object is moving away from where it started. A decrease in the position means that it's returning to where it's getting closer to / returning to where it started. And a flat line means that the object is not moving. Let's move on to the velocity graph. Velocity can be increasing as seen here, can be decreasing as seen all right here, and it can be constant, as in he's running at the exact same speed. So first Mario, he's speeding up, then he's running at the same speed. Then Mario is slowing down, and then Mario is speeding back up right here. Alright, let's move on to acceleration. Don't forget that acceleration is any change in velocity. Think of acceleration as the velocity is either changing or it's not changing. So here, the acceleration can be positive or it can be negative. He can either be speeding up or slowing down. So right here, the acceleration, he's speeding up. Then Mario is running at the same speed, and so the acceleration, he's not changing, he's running at the same speed. So it's going to be 0. And all right here, he's slowing down. The acceleration is around -2, right? He's slowing down. Then right here, he decides to speed up again. Acceleration's positive, he's speeding up. Then Mario stops to take a break. Acceleration is 0. He's no longer changing velocity anymore. Over here's a quick hint. You're expected to know always that velocity is equal to change in position over time, or delta x over t, and acceleration is always equal to change in velocity over time, or delta v over t. Alright, so the graphs relate to each other in very specific ways. It's important to know the definition of slope, which is rise over run on the graphs. Now, the slope, or the derivative, of the position graph is what creates the velocity graph. So now, right here on distance, you can see right here the slope is positive, right? Let's pretend that right here it has a slope of about 15. Y is equal to 15x per se. Now what that means on the velocity graph is that means right here it's 15. That's what you're plotting on the next graph, right? Same when we move on to the acceleration graph. The slope, or the derivative, of the velocity graph is what equals the acceleration graph. So right here, remember, a straight line on a graph means that the slope is 0. So right here, the slope is 0, which makes sense. Over here on acceleration, the acceleration is equal to 0, right? Now, over here we have a nice diagram that explains this. So the slope of the position time graph is what makes the velocity time graph. And if you take the slope of the velocity time graph, you get the acceleration time graph. Now, these also can move backwards. So the area under the acceleration graph gives you total change in velocity. So if you take the area of everything on this graph, all the area between any line in the x-axis, so here, here, and here, you get the total change in velocity that Mario had between 0 and 30 seconds. Now, don't forget that this can also be done from 0 to a specific point in time. 0 to 15 seconds, we could take the area under the graph just for there and get the change in velocity from just 0 to 15 seconds. Now, the area under the curve for velocity means the total change in distance, or the displacement. Same thing applies here. We can go from 0 all the way to the end of the graph, or you could go from 0 to a specific point in time. If we want to know how far Mario traveled just from 0 to 10, we would take the area under the curve from 0 to 10 seconds. Alright, now motion graph problems can get a little tricky. You need to be able to comfortably go from position to velocity to acceleration. Given the position graph, be able to know what the velocity graph would look like. From the velocity graph, be able to know what the acceleration graph would look like. So you have to be able to quickly understand how the slope relates to the next graph. You have to also be able to go backwards. Given the acceleration graph, draw and understand what the velocity and position graphs would look like. So now, we're going to give you a little sample problem right here. I'd recommend pausing the video and try this on your own. Right here is a velocity graph. I'd like you to draw the acceleration graph from this. Quick hint over here, remember, you're graphing the slope of this line, right? So, for the acceleration graph, we have right here, this is going to be negative slope, right? And slope is always rise over run. So right here we go from rise, we go down 4 over 4. So negative 4 over 4, we have a slope of negative 1 right here. You can break this into chunks any way you want, right? So then that means on the acceleration graph from 0 to 4, we would graph negative 1, a line at negative 1. That would be your graph of the acceleration. So go on, continue this for the rest of this graph. I would pause it and do it, because on the next slide is going to be the answer. And here's your answer. So right here we have negative 1. Then we see the acceleration jumps to 0, goes back up, and you can rewind the video and compare the graphs. Alright, next we have the kinematic equations. There are 4 kinematic equations, and they are derived from the position, velocity, and acceleration graphs that we just saw. There's a lot of math that goes into that. You don't have to know how they're derived. You just have to know the kinematic equations. You might not actually have to memorize them. You might be given an equation sheet, but you have to know how to use them. And so one thing that's very important for knowing the kinematic equations is that there's one variable missing from each of these. And this is going to be important to remember when manipulating these equations while use them to solve word problems. So in this first equation, let's quickly go over the variables of each of them. V is equal to velocity at a specific time. It's also often referred to as V final. You'll know the velocity at the final time, and so that is why it'll be V, and you'll oftentimes see a little f right here. Now V initial, or V0, this is the starting velocity that you have. 0 refers to 0 seconds, or the time where the time interval starts. A is acceleration, T is time, and delta x you see here is your displacement, or how far you traveled over the course of time. Now, what each variable is missing. Right here you can see this equation is missing displacement. So if you have a word problem that you don't need displacement for, you're going to use this one. This one's missing acceleration. This one's missing velocity, or V final. V initial is still here. And this one you don't have time. So now there's a few things that you're expected to know while using these equations. velocity is equal to change in position over time. Acceleration is equal to change in velocity over time. So now this one's a little tricky. At the peak of direct trajectory, the velocity is always 0. Imagine really quickly for me, you're throwing a ball or football into the air, right? It's going to make a trajectory like this. It's going to make a parabola. Well, at the very peak, at the highest point of that parabola, the velocity is considered to be 0. The velocity up and down is considered to be 0, your y velocity. So it's going up, it's going up, it's going up, and then for a split second in time right here, it is actually not moving in regards to the y-axis, and then it starts going down again. This is not true for horizontal velocity. It has a constant horizontal velocity, and we'll get into that in another video. Also, always remember, gravity's acceleration is always negative 9.8 meters per second squared. All right, so let's go on to these practice problems real quick. We're just going to quickly go over. I highly recommend solving these on your own to start getting used to these equations. But right now in the video, I'm just going to ask you, and I want you to think about what equation you would use for each of these. So First question, an airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. All right, so what do we have here? We have acceleration. We have the time traveled before it lifts off the ground. So what equation would we use here? We can also assume from this word problem that the airplane started at a standstill, as if you were actually taking off in an airplane. So quickly look at these. We have acceleration, we have the time that it traveled, we want to know the distance that it traveled. We can assume v0, the initial velocity is 0. So you can pause the video because I'm about to tell you the answer. The correct one would be 3. So we want displacement, we have acceleration, we have time, and we know that the initial velocity is 0, so this essentially cancels out, and then we can get our answer. All right, so for number 2, a bike accelerates uniformly from rest at a speed of 7.1 meters per second over a distance of 30.4 meters. So we have the initial velocity, 0. We have the final velocity, 7.1. And we have the distance that it's traveled. So look at your equations, pause the video, and try and decide which one you would use. So for this one, we would use 4. We have the final velocity, we have the initial velocity, which is 0. We have the distance traveled, and we want to know the acceleration. All right, so for question 3, a car traveling at 22.4 meters per second stops in 2.55 seconds. Determine the skidding distance of the car. All right, so we have its initial velocity. We have its final velocity, which is 0 because we know it stops. We have the time that it took to do that, and we want to know the distance of the car. So quickly look at these. And tell me what you think you would use. So I'll pause the video. So for this one, we're going to use equation 2. We want to know the distance traveled. We have v final, we have v initial, and we have the time that it took to do so. So that's going to be the correct equation. All right, so then we have one last one. Also, here's the answers to the ones on the previous slide. I recommend going back and doing the work for those. Question 4. If Michael Jordan has a vertical leap of 1.2 meters, then what is his takeoff speed and his hang time, the total time to move upwards to the peak and then return to the ground? So this one is very tricky. We have to use 2 equations for this one. I would sit down and try this one. And don't forget, one of the hints that you need to use for this one is that at the top of Michael Jordan's trajectory, so he jumps up into the air right before he starts moving back down to the ground for a split second in time, his velocity is technically 0. And so you can use that as the final velocity in your equation when figuring this problem out. All right, so pause the video and try and figure that out because I'll tell you the answer here. You have to use equation 4 and then equation 1. You can go on and continue that problem if you'd like before looking at the answers. So here's a quick recap, the slope of the position graph makes the velocity graph. The slope of the velocity graph makes the acceleration graph. The area under the velocity graph is total displacement. The area under the acceleration graph is total change in velocity. And the kinematic equations are derived from these graphs, and each one is missing a different variable. They can be manipulated in a multitude of ways to help you solve your problems. Hope this video was helpful. Please recommend to us any practice problems that you'd like us to go over, and have a good one.